Welcome back, folks. Here's another source conversion example. This one's going to be bigger. This one's going to be uglier. This one's going to be more educational. I'm excited. I think this is my 104th video, 105th, something like that, just for this class. Can't wait for the semester to start, and then I can talk to you in person. That'll be fun. All right, so it's a little bit bigger, it's a little bit uglier. We're looking for I out, which is labeled right here. Not in a totally pretty way, but let's steal this again for safekeeping. We got to play the anything in series, anything in parallel game. I'm usually asking you to identify these, so I'm really hoping that you're following along in these videos and you're trying to find these relationships yourself rather than just listening to me do this. It's a lot more fun when it's interactive, and it's way more fun when you get them wrong, and I draw it anyways. So I kind of missed that. Hopefully we'll get some of that in the live session when we'll do even more examples and we'll work problems together. Really looking forward to that. Okay, so anything in series. Let's see, these two are in series. So once again, I gave you kind of a softball to get you started. Okay, so these are in series. So we can combine those. 1 plus 4 equals 5. I think we can handle that one. Anything in parallel, and we got to be a little careful with this one. A lot of people correctly identify the 6 and the 3. Okay, that these are in parallel. Okay, they're separated by this current supply, and they are in parallel with the current supply, but we can't combine those yet. We can convert them, right? We can make that combination, that parallel combination, as we redraw. Something that tends to catch people in this one, so I'm going to mention it. You may be looking at the 5 amp and the 3 amp and say, hey, those are in parallel, and you'd be wrong because of this 5 volt supply. Okay, this node here is different than this node over here. So the 5 amp and the 3 amp are not in parallel electrically. They don't share the same 2 nodes. Okay, so let's make this parallel combination and this series combination and go from there. So we got to redraw this as a single resistor, and it's going to be 4 ohms plus 1 ohm equals 5 ohms. Okay, these two are going to get combined, so we can just knock that one out. The noises totally help. This is then going to be, oh, I should have left that, 6 in parallel with 3, and that's equal to 2 ohms. Okay, so it's already smaller, just making those simple combinations that I think we already knew what to do with that, but it gets us a little further on the way to making some conversions. Okay, so anything in series, I don't see anything in series here. Anything in parallel, I see a current supply and a resistor, and I see a current supply and 2 resistors, but I can't combine those. These two are in parallel, but if I combine those, the 5 ohm over here and the 7 ohm, I'm going to lose that I out. Okay, so I can't make that combination because that resistor has the current of interest for us. Okay, so we're left with doing conversions, and I usually ask people what conversion they want to do, and one of them is a dead end, and one of them isn't. So hopefully you're looking at it, and if you can get good at picturing this in your head, then maybe you can see the dead end beforehand. Let's go ahead and do the dead end first, because I do think there's some educational value in understanding that just because you can convert something doesn't mean you should. Okay, so let's copy our current circuit, and the dead end conversion is this one over here. Okay, if I take this Norton equivalent and I convert it to a Thevenin equivalent, okay, then we're going to drop out this. Okay, and we're going to replace it with a Thevenin equivalent. All right, so that's going to be a resistance and a voltage supply in series. So the resistance is just 5 ohms, that comes up, and the voltage is 3 amps times 5 ohms, which is equal to 15 volts. Okay, now here's what, it's a perfectly good conversion. It is an equivalent circuit, nothing wrong with that. The problem is it doesn't move me forward. By moving that resistor up, that resistor is not in series with the 7. It's not in parallel with the 2 over here. It didn't buy me anything. Okay, this is a dead end. So what color do you want to be dead end? Dead end, like a dead end street. Okay, we got to turn around, we got to go back, and we got to find another path. And that's what we're going to do. So this one came from converting that. Okay, so the one that is going to work out nicely here is that Norton equivalent. So that one's good. So I cut that. Well, we're going to have to do a lot of erasing here. Okay, so bring that down and hopefully erase, but not too much, right? Stand by, folks. I'll clean it up. All right, it's a little better. But we're going to take this Norton equivalent and we're going to turn it into a Thevenin equivalent. So it's 5 amps and 2 ohms. Let's knock out enough of that there. Okay, and we're going to turn it into a Thevenin equivalent. So let's get a voltage supply with a series resistance. I just said the values and I already forgot. You should yell them at your screen now. I think this was a 2 ohm and this was 5 amps. And the 2 ohm is going to give me a 10 volt. I got brave. 5 amp 2 ohms. Nice. Yay, short-term memory. Good stuff. Okay, so making that conversion equally valid, but when I reconnect it to the rest of the circuit, which I'm treating as the load, these voltage supplies are now in series, right? This one is in series with the 2 ohm. This one is in series with the 2 ohm. So therefore they're in series with each other. So I can combine those. Right, so that and that are in series. So if I go bottom to top, that's plus, and then as I keep moving around, I'm moving negative to positive, so that's a plus as well. So we did this in videos gone by, but we can combine those, and it's going to be 10 volts plus 5 volts equals 15 volts. And this is 2 ohms. Okay, so I got rid of that 5 volt on the top. And by getting rid of that 5 volt on the top, more stuff is going to end up in series and in parallel. So I need the rest of the circuit. Grab all that. I usually redraw these. Why would I do that when I can cut and paste? Right? Wire that there, wire that there. Not pretty, but doesn't matter, neither am I. Okay, so this is our 5 ohm, just to make it a little cleaner. All right, anything in series? These two things. It doesn't buy me anything for combining. Anything in parallel. These 3 things, I can't combine these 2 because I lose I out. But I do have a Norton equivalent here, and I have a Thevenin equivalent here. One of them is going to be more useful than the other. I'm not saying, no, one of them's a dead end, one of them's not. So take a moment. Do I want to convert the Thevenin equivalent, or do I want to convert the Norton equivalent? Which one's going to move me further down towards finding I out? Okay, so hopefully you've thought about that. What I'm going to combine, after I take a snapshot, what I'm going to convert is the Thevenin equivalent. Okay, because if I do that and I reconnect the load, I'm going to have a lot of things in parallel that I can then work with. So let's get a copy of that circuit. 15 volts, 2 amps, right? So let's do this. Buy some real estate here. Get rid of some of my kind of janky wiring. And make it a Norton equivalent. Okay, the 2 ohms moves down. The 15 volts and the 2 ohms convert to a 7.5 amp. All right, wire that up to the load, which is just the rest of the circuit. And we're getting closer, right? Whew, it was a big one. I told you it was a big one. I didn't lie to you. All right, anything in series. Not a single thing in series in this circuit. Anything in parallel. Yeah, a handful of things. We've got the current supplies are in parallel, right? And the resistors are also in parallel. Okay, so I'm going to make that combination, and I'm going to make that combination in the next circuit. Both of the current supplies are pointing up, so this is going to be 7.5 amps plus 3 amps equals 10.5 amps. Okay. 2 in parallel with 5 is some horrible, horrible fraction. It's going to be less than 2. It's going to be greater than 1. .43 ohms. Okay. That's an omega, believe it or not. It's a slightly better omega. Okay, connected to the rest of the circuit. The only thing left in the circuit is the 7 ohm. Okay, and that's where I out is flowing. So we label it as such. Okay. Anything in series? Nope. Anything in parallel? Yeah, but I can't combine them because I'll lose I out. Okay, so anything I can convert? Yes, there is. This is a Norton equivalent, and we can convert that to a Thevenin. So this is a Norton, and we're going to convert that to a Thevenin, and then we're going to reconnect it to the rest of the circuit. And hopefully you see the light at the end of the tunnel. If you didn't before, at least when I draw this. 1.43 moves up so that it's in series, and this is going to be 10.5 amps times 1.43 ohms. And that's equal to something. I'm not doing that in my head. Times 10.5. Oh, that's dirty. It's 15 volts. It does work out nicely. Okay, 15 volts. Anything in series that I can combine. Now, finally, I can combine something with the 7 ohm because it's in series. Okay, only because it's in series, they're going to carry the same current. I don't lose I out. I do lose this node. So if I was looking for V out, I couldn't do it, right? Because this node would disappear. Luckily, that's not the case. Yay, textbook problems. Okay, so redraw this one as a single resistor. 1.43 plus 7 equals 8.43 ohms. This is 15 volts, and I'm interested in I out. So the last thing we've got to do is use Ohm's law and say I out is equal to 15 volts over 8.43 ohms. What does that work out to be? 15 divided by 8.43. 1.78, we'll call it 1.78 amps. Whew. Okay. Horrible way to solve a circuit. Wonderful way to reduce the complexity. So what did we start out with up here? 1, 2, 3, 4, 5 meshes. Let's play this game. Meshes, nodes. Look at me being lazy. I didn't want that. Look at me being lazy. Okay, so what did we start out with? We started out with 5 meshes and 1, 2, 3, 4 nodes. Okay, we made some combinations and we ended up with 1, 2, 3, 4 meshes and 1, 2, 3 nodes. Okay, here we got down to 3 meshes and 1, 2, 3, 4 nodes. Ooh, we backslid on the nodes, but it's getting smaller. If you keep at it, keep combining things, eventually you'll get something reasonable. So we got 3 meshes and 1, 2, 3, 4 nodes. So not much of a change there. Okay, 1, 2, 3 meshes and 1, 2, 3 nodes. Okay, getting better, making a little progress. Here we have 1, 2, 3, 4 meshes. Uh-oh, went backwards, but we only have 2 nodes. 2 nodes. Okay, down to here, 2 meshes, 2 nodes. Getting smaller, 1 mesh, 3 nodes, and then finally what I was going for, which is 1 mesh, 2 nodes. Behind my head. Oh, chair's still there. There you go. Okay. It reduces complexity. That's really all we're going for. I am taking it down to Ohm's law because I want you to follow along and make sure you get comfortable making these conversions, redrawing it as you need to, getting it right. Okay, one more example. This one's going to have a dependent supply in it. I know you're all excited about that, but then we get to move on to new stuff. Okay, stay tuned and good luck.